Thanks, Jay, and hello, everyone. It is a pleasure to be able to be with you here today to discuss this really interesting project that we're getting to work on here at Greenland Peterson regarding the Bahia Honda Bridge down in the Florida Keys. We're very fortunate to be able to come alongside the Florida Department of Environmental Protection for the restoration of this historic structure, and we've got put together a great team to work on it. The webinar is going to be divided up into three different parts. And the first part, I'm just going to give you a brief history of the structure to give you an idea of its historic importance, its significance, and then to also give you an idea of, first of all, why it even exists, but then also why it exists in the state in which it currently is today. Then we'll move on to some of the preliminary investigations that were done for the structure in the field, the results of our preliminary analysis, and how we came to our preferred alternate that we ended up pursuing as far as the design. We're currently in the midst of the design for this structure, and as moving from the preliminary stages into the final design stage, we actually shifted our analysis from a different software package to Midas. So the last part of this presentation will be touching on a few of the features and abilities in Midas that we felt were worthwhile for the sake of switching over for the final portion of the project. Henry Flagler was a northern industrialist. In 1870, he co-founded Standard Oil with John Rockefeller and Samuel Andrews. By the end of that decade, Standard was refining about 90% of the oil in the United States, and they eventually gained nearly complete control of the oil refining and marketing industry in this country. To give you some idea of the enormity of the Standard Oil Trust, when it was broken up in 1911 as a result of the Sherman Antitrust Act, it was divided into 34 separate companies. And in amongst those 34 companies were the companies that would become Amoco, Chevron, Exxon, and Mobil. In the late 1870s, Flagler started traveling to Florida in the winter for the sake of his first wife's health, and he ended up falling in love with not just the state, but the development opportunities that the state presented. By 1885, he had stepped down from his day-to-day responsibilities at Standard Oil, and he started up in the St. Augustine area purchasing short-line railroads and improving their traffic capacity and improving them to withstand, be able to use higher loads, and then also extending them down towards the south, building new lines. And then in addition, all along the route, he built lavish hotels in Jacksonville, St. Augustine, Ormond Beach, Palm Beach, and Miami. By 1896, his railroad had reached the southern end of the peninsula, but he wasn't quite done yet, because by 1904, he had decided to set off on a new plan, which was widely considered to be impossible at the time. He wanted to extend his railway 128 miles beyond the southern tip of the peninsula to Key West. Now, Key West at the time, at 20,000 people, was the most populated city in the entire state, and it also possessed the closest deep water port to what was then the proposed Panama Canal. In addition, the railway was going to provide increased opportunities for trade with Cuba and with the rest of Latin America. Flagler self-funded the venture, which I've seen estimates for it ranging between $20 and $50 million, which brought into current currency that ranges somewhere between $500 million to $1 billion for the total cost of the project. His construction engineer, William Crone, surveyed several routes, quickly landing on the decision to follow the islands around rather than attempting to cross longer stretches with open water. The project has 17 miles of bridges and 20 miles of fill embankment. But of all that, there were 3 locations that posed the greatest obstacles. First, there was a 2-mile long crossing from Long Key to Conch Key. There was a 7-mile long crossing from Knights Key to Little Duck Key. And then what was the deepest crossing on the entire project, the 24-foot deep, mile-wide crossing at Bahia Honda, which from the Spanish of Bahia Honda means deep bay. With these particular site conditions, Bahia Honda is the only location along the route that utilizes through-truss structure, and at over 5,000 feet long, it has an almost 250-foot long Parker truss span, which is surrounded by 26 Pratt truss spans, and on the western approach there are 9 plate girder spans. The shorter spans use riveted connections. The longer Pratt and Parker spans use pin connections, which made it the longest pin-connected truss bridge in the country. Despite 3 hurricanes and hundreds of lost lives, the project, which at times employed nearly 4,000 simultaneous workers, was completed in 1912, and just 16 months before flag wave passing. At the time, the railway was being hailed as the 8th wonder of the world, which was a nice step up from when it was being called flag wave falling at the beginning. The railway functioned until the Category 5 Labor Day hurricane of 1935. The Florida East Coast Railway, which was bankrupt at the time, was not able to fund the repair to the extensive damage, and as a result sold the remaining rail infrastructure to the state of Florida. The state had already begun construction on their overseas railway, and they ended up shifting the alignment in order to be able to reuse the remaining rail infrastructure that was still in acceptable condition. At Bahia Honda, due to insufficient clearance between the trusses, they ended up building the deck for the 2-lane highway along the tops of the trusses and constructed approaches supported on pile vents to elevate the traffic. The approaches consisted of 2-span steel stringers, each placed directly over corresponding H piles. The highway ended up opening on March 29, 1938, as the southernmost segment of U.S. Highway 1. With the widening of the overseas highway to a 4-lane divided highway in the 1970s, traffic was closed off from the Bahia Honda Bridge, and it was added to the National Register of Historic Places in 1979. Since then, access to the structure has been limited by the removal of a span from each end of the bridge. However, on the east end, it was the 3rd from last span that was taken out, leaving the approach spans and the first 2 truss spans available as a pedestrian overlook. The overlook, the truss spans specifically of the overlook, were closed off to pedestrians in 2015 due to extensive deterioration of the structure and safety concerns for the public. And so we've been fortunate enough to be selected to assist the Florida Department of Environmental Protection with the restoration of this structure. And we were able to bring along facility inspection and transportation engineering and underwater engineering services as part of our team, and they did a fantastic job with the field investigations and in giving us a better picture of the level of deterioration that exists with the existing structure. FIT went out to the site on June 2016 Obviously, the picture on the right is a different job of theirs, inspecting a bridge hit, but on the left you can see Sonia Johnson climbing the structure. She performed the inspection of the steel portion of the structure and the concrete deck. And since she climbed the entire structure, she was able to get hands-on inspection with every component. And then I'm pretty sure she probably took multiple photos of every component, because in addition to the report of findings that she sent us, she provided us with a CD of over 1,100 photos, which really was vital in our getting a good understanding of the deterioration member by member, and helped us with developing our plan for modeling and for coming up with our recommendations. Here you see a sampling of the photos that she sent us. On the left side, you see a couple photos from the approaches. Top left is one of the H piles at a vent down where it meets the concrete jacket that goes into the ground. You can see that the section's almost entirely gone. Below that, you see one of the stringers at its support, and in addition to being able to see straight through the stringer, you can see that the clip that's supposed to restrain the stringer but allow for thermal movement has been completely seized up due to rust. And then on the right, you see a couple of photos from the truss spans, both top cord and bottom cord, where you see the extensive corrosion and the massive section loss that exists out there. In 2016, UESI went out to the site and performed the inspection of the piers and the abutment, both above and underwater. And we were pleasantly surprised to find that these portions of the structure were actually in much, much better condition than the steel. We were especially pleased considering these things are over 100 years old. They did find cracking, as would be expected, cracking wide enough for chloride infiltration, but there weren't any locations where they detected any corrosion bleed out coming from these cracks. Pretty much all the locations where there was corrosion was limited to support rods, well, rods that were protruding from the structure that we're pretty sure were there to support the formwork during construction. On the underside, there were also some locations of isolated port consolidation, but again, not too surprising considering when and how the structure was built, and you know, in general, it's in very good shape. On the underside, there are some areas of undermining due to scour. You can see a picture of that over on the right, and in general, it wasn't too bad. There probably is some minor amount of loss of capacity, but considering that the structure was designed for heavy rail and it's currently functioning as the pedestrian overlook, whatever minor capacity loss there might be there isn't going to really affect the safety of the structure for its current use. Pretty much everything that was found in these areas just amounted to necessitating continued monitoring during the regular inspections and maybe some minor maintenance work. But in general, this stuff was all really good. So based on the information we got from the field, we created our preliminary model. Going through all the photos and the report from FIT, we were able to develop some criteria based on the amount of section loss that was exhibited on average based on a member-by-member basis. We applied that to our model to see where we ended up, and it turned out the structure wasn't safe for even the pedestrian loading and would require some strengthening. So we also looked at what it would take to get the members that needed to be strengthened up to a section that would actually be safe for the public. As part of our report that we delivered to the DEP, we looked at multiple alternatives. Obviously, no build, but that wasn't really an option, just due to safety concerns of the bridge starting to fall apart. We looked at field rehabilitation, disassembly, and then shipping the structure off for shop rehabilitation. And then we also looked at the potential of doing a replacement, essentially a replica structure. And then in addition to those 4 options, we looked at combinations of each of the 4 to see what made the most sense. Having presented our report to the DEP and then in discussions with them, we ended up deciding to move forward with a replica structure. Essentially, we're planning on reusing the existing piers and abutments, and then we're going to replace steel portions of the structure with a structure to look essentially identical to what's out there, but utilizing modern sections to replace all the existing built-up sections in order to facilitate, greater efficiency in fabrication and construction, but then also to provide the DEP with a structure that's going to be easily maintainable for the foreseeable future. And you see at the bottom there a few of the typical types of sections that existed on the bridge. In general, they're plates and angles that have been all riveted together, and we're going to be replacing these with H-piles and channels and plate girders. So as I mentioned before, we're in the midst of design here, and the preliminary portion of the design has been done in a different software package. Looking at some of the features that were available in Midas, we decided that that we would shift over to Midas for this next stage in design. We felt like some of the features that it made available to us would help in our analysis and also provide greater efficiency in that analysis. So for the rest of this, I'm just going to touch on a few of the features that we found particularly helpful that helped us in that decision-making process of shifting over. Specifically, I'm going to touch on the import functionality and a few of the aspects of the import functionality that give you a little bit of a leg up once you have the model in it and can get started with assigning your members. We're also going to look quickly at construction staging. I feel like the program provides a pretty straightforward setup for construction staging that works pretty well. And moving on to some of the reporting for the steel design checks that are pretty detailed and provide a manner of efficiently getting to the information you want to get to. And then we'll wrap it up with how you can deal with some custom sections inside Midas, which on a structure like this, you've got a lot of sections that aren't going to be readily available in a drop-down menu. You're going to have to come up with maybe a few build-up components, and then there's the way Midas deals with it is actually pretty efficient and helpful. So to start off, we've got our 3D model in AutoCAD that we developed. As you can see, all the individual components have been put onto separate layers so that we could segment them out, and that actually comes in pretty handy once you go to bring the model into Midas. So from this model, we export the DXF file and we bring it into Midas. Let's make sure this is in inches. So pretty straightforward. You created your new file, just import your DXF. So when this window pops up, you browse to the DXF file, and this is where having created all those different layers comes in handy. You can come over here and selectively bring in what you want, which is great if you've got a model that has additional information in it that you don't want to bring in. You can be pretty selective selective about what you actually transfer over into Midas. So having selected all of those, you can come in. These properties, you can just leave them blank and deal with them later, but we'll just get them knocked out now. Obviously, you can come in and add your material properties, steel or concrete or whatever. Your section, same thing, come in and add your different types of sections. Since we've already got a file, we're just going to import everything we've already have created in the other file. So it's pretty straightforward. And so now we've got everything in there, we just hit OK, and it pops your model in. So you'll notice over here the materials and the sections that have been defined and assigned to something appear in black. The ones that have been defined but not assigned to anything come up in blue. So as you can see, when it pulls the model in from the DXF file, it just assigns everything to your first material and your first section. But one of the other things it does that I find incredibly helpful, all those different layers that you were able to pull in, it automatically adds those to structure groups. So you can go through and say there's 35 stringer elements, you can just select every single one, keep them all together. It allows you the opportunity to maybe you want to look at them specifically, or and the grouping actually helps quite a bit as you're going through your model and trying to pull results and look at what's going on. But it also helps with just assigning properties, because like I said, everything came in as an A70950, but you can go through and just select all your bracing and right-click, select, come over to A36, right-click, assign, and now you can see that went black. All of the numbers are now assigned to A36, and your other numbers are all still A709. In the same fashion, you can come over and select your diagonal bracing, and say we want to make this a double angle. We just come over and assign it, and you can see it updates. So obviously, with this number of members, it would take quite a bit of time to go through one by one and assign them a material and a section. But really, with the way that Midas lays it out, I find it to be just about as efficient as you can get it. So from here, we're just going to switch over to a file that has a bit more defined in it. And as I mentioned before, we're still working on this job, so by no means is this a final model, not even our most recent model, but it's a good one to just show what these particular features. So here you see we've assigned all our member properties, all our section properties. We've maybe shifted a few things around to get them in a better position than where we had it in our AutoCAD model. With members like the orbital diagonals, we've rotated those around to get them in a good orientation, and okay, and so coming over here with the materials, you can see they've all been assigned to something, except the concrete that actually comes into play with the construction staging. We defined a dummy material, which essentially consists of just concrete with no weight that we've assigned to these dummy beams that we created in order to distribute load. We've also got another dummy beam just for the barrier to represent the barriers. So we've got our supports defined. Our beam end releases are defined. When you bring your model in, you import it, pretty much every node is going to have full moment transfer. So locations where you want a pin connection or you want some sort of reduced restraints, you're going to have to define those. And so that's been done here. And then there have been a number of bridge links created to to transfer loads from one node to another. Got our loads defined, and we've got an H10 vehicle on there. So essentially all our structural components and our loads have been defined in the structure. But in addition, we've created some more groups. So we've got the groups that were initially created on the import. We also have a number of boundary groups, both for the rigid links, but then also for the supports and for the end releases for the beams. And then we've also got some load groups that were created for the loads that the structure is going to experience. The way the construction staging functions is everything's defined based on a group that gets activated or deactivated. So if you have a load or a boundary condition that is not in a group that gets activated, it may as well not exist in the structure because it's not going to be taken into account when the analysis gets run. But here for the construction stage, you can just come over to that button, and when you first set it up, this is going to be blank, and unlock the model. This is going to be blank, and you would hit add, which would bring up a window just like this. Like I said, I feel the construction staging setup in Midas is pretty straightforward. Essentially, you're going to name your stage, duration of your stage, and then in this window, you're going to get a list of the different groups that you've created. So essentially, these structures groups will show up in this window, and then same for the boundary groups and the load groups. And based on what you are looking to activate in each stage, you would move it into this window. Whatever you want to deactivate, you would move into this window. So in this first stage, we're creating the base steel portion of the structure. So we've activated everything except for those dummy beams I had discussed earlier. We're activating all of the boundary conditions, and we're activating the self-weight of the structure. Moving on to the next stage, you end up activating the wet concrete loads that we've applied to the structure. And then in stage 2.2, where the concrete has hardened, we're activating the dummy beams that we've defined, and then deactivating the wet concrete load. Stage 3, you've got your barrier loads activated in addition to your dummy beam for your barrier loads. And then stage 4 is essentially just your long-term structure with those loads. In addition to defining your construction staging, you also need to, for any composite sections, you can see here the stringers along the top have been defined as composite sections. And so you need to come in and define your composite section for the construction stage. Again, this would be empty, you would hit add, but essentially you come into this window and you select which stage the component is going to be activated in initially. You select which component you're looking at, and then down in this window, you tell the program when to activate each portion of the composite section. So element 1, we're going to be, you can deal with these as either the element itself or its material. So we're going to deal with it as an element, activate it in the active stage, which we've called out as stage 1. And then the second portion of the composite section, you are going to, we're going to deal with it as the material. And this is where that grade 4500 concrete comes in, that we've defined it as being that material. And that ends up getting activated in stage 2.2. So you would do that for each one of your different composite sections that you've defined to let the program know when to go ahead and activate those during construction staging. So now that we've got everything defined, we can run our analysis. And that just takes a few seconds. And so with that done, we can move on to some of the reporting for the steel design component. Coming over to design, this is where you can find all your different common parameters, your unbraced length, your K factors, slenderness ratios. You know, and you can do this. You can define it globally, but you can drill down and define each of these properties on a number by number basis, and then come in and run your steel code check. And so you can see there's a couple angle sections that have come up as not being good. You can hit double arrows to expand it. And I think this view actually provides a wealth of information for the small amount of space that it takes up. You can get, essentially this is displaying when it comes up on a member type and element type basis, controlling number for each type of component. You can also switch it to a member view where it is actually going to show you all of the members. In general, you can just look at the controlling ones for each type and sort it by good sections, no good sections, and it's going to give you the combination ratio, shear ratio, your unbraced lengths, your CV values, what K value is assuming. So you can look at all the base parameters and get a good idea of if it's looking at the number correctly and where is that number, how far over is it, just from this one screen. But then you can drill down even more. Say we look at this angle, you can pull up a summary view that is really just the load combinations and then essentially the same information you got on that first screen, but in a nice printable format. You also have this graphic view that allows you to take a look at the actual section properties, the loads that it's experiencing, the forces in the member, and then each one of the checks, it shows you whether it's good or no good and where your ratio is sitting. So a good quick snapshot of any particular member you want to look at. And then if you want to drill down even further, for each member you can pull up this detailed view, which allows you to look at the load combinations, section properties, the loads that are being applied, and then it actually goes through all of the design checks, providing you with the reference that it's using from the particular code you have set, the ratio that it's coming up with, and whether it passes or not. And going through, you're looking at your axial strength, your flexural strength on the major axis, your lateral torsional buckling. So you can get a good snapshot of what checks are being performed, what are the references for that check if you want to go and dig into it a little bit deeper, what section properties is it using, what loads is it using, so you can get an idea of, all right, well, did I somewhere mess up with some of my fixity or with how I've set up my model, and do these properties and these loads make sense for what I'm trying to do? And then if they do, you can look at the code references and figure out in more detail what's going on with numbers that are failing on you. But then say from this window, if you want to take a look at replacement sections, you can just come up to change. You can hold steady within a certain range, any property for the element you're looking at, and then what range you want your ratio to be for the code checks, and then just have it search, and it'll pull up all of the members that work for that section to be replaced too. So you can even change if you want to go even lower to pull up more sections. So really quick way to if you're certain that all of your design parameters are correct and your loading is correct, a very quick way to go in and figure out which section do I need to replace what I've got to get something that works in there. So let's say you want to replace it with a 6x6 and you can just hit change and close. And you can see it updated the design check, and it says OK now. The one thing you'll notice, this is section 10. Section 10 here is still showing 5 by 5. So if you want to actually update it into your model, you come over to update, you select the section you want to update, and now you can should have updated. I don't know why it didn't. But anyway, so with these code checks, it's a very quick way of the way that Midas displayed it is a very quick way to be able to get a good idea in general how your structure is performing, but then it's very quick to drill down, find specific members that aren't working, see what code checks aren't working to figure out if maybe there's something you need to tweak in your analysis, and then if not, find a section to replace it with. So with that, we're going to move on to the last item, which on a structure like this, there are a lot of sections that are not going to be easily found. Either angles and strange orientation, or maybe channels that are put together with a plate on top or something like that. And what we're going to look at specifically is the bottom chord of the structure. You can see here what we've got defined right now is an H file that's turned on its side. What's out in the field is a series of plates and angles that are riveted together to create pretty much the same shape, except that there's a gap that runs straight down the center between the two portions. So, we could deal with it with a standard H file just by cutting holes in the web all the way down. But what we're going to look at here is, what if we take a couple WTs and turn them on their sides, and that way actually get even closer to the existing shape. And fortunately, Midas actually makes that a pretty straightforward process. You can come over to Tools and open up the General Section Designer. Coming over to Shape, you can right-click and add Basic Shape. We're going to add a T-section based on the AISC code, and we're looking at a WT 6 by 36. We'll define the material for it. And then changing this to chips and inches. We'll change our insertion point to -4 inches with a rotation of -90. And here's our first part of our section. So double-clicking, we can select that, and it's easy as hitting Control-C, Control-V to copy and paste. And we can then edit the new section that came in and change its insertion point to 4, and then we'll just rotate it the other direction and hit OK. And now we've got essentially the section we're looking for. One thing I've come across as an issue is with these custom sections, and it seems Midas doesn't like when there's an open gap like that, like we have in here. The way I've gotten around that, and maybe when Jay comes back, he'll tell me there's a better way to do this, but this is how I've done it, is you can just add another basic shape, and I'll add in a user-defined rectangle and just give it a tiny thickness and a width to bridge that gap and bring it in. And then we can select our numbers and merge them. We can do the same with these. And now we've got a single shape that bridges across that gap, and we can bring it to Midas. This button up here allows you to create your link to the open model. So simply clicking on that, it links over to the Midas model. You can see it went from red to green to show that it's linked. And in the text box, you can type in the name of the section, there's section 1, and hit export. You can see it was brought into Midas there. And so we can select our bottom chord, and we can assign it to that new section. And since we had the H file in there, but we had it rotated 90 degrees, when it brings in this new section, it's now rotated 90 degrees as well. But that's easy enough to fix just by going to Element and then Change Parameters. And this is the window where you change all the individual parameters for a component. You can change the material ID or the section ID. We're going to change the element local axis, and we're going to change it back to 0. So you just hit apply, and so you can see the section we created that's been brought into Midas, and we can rerun our analysis on it. Now, when I was running the steel design checks earlier, you may have noticed in this message window there were a number of sections that were coming through that said that they couldn't be analyzed due to using the steel code checks. And those are either going to be your concrete sections, or for a lot of those are the built-up sections that have been created in the section modeler and brought in. Midas doesn't actually check those within the program itself, but it does give you the capability of bringing that back into the section module, the section, the section designer in order to check it over there. So now that your analysis is done in here, you can reselect that bottom chord, and you can see here in the selection window that that those particular elements have been selected. Going back into the section designer, you can see that those same elements have popped up in this window, and all you have to do is hit import. And it asks you which load combinations and which parts of the section you want to pull in. For this, we'll just pull everything in, hit OK. And as you can see, here's the section we initially defined, and here's the section that got pulled in from Midas with all your load combinations in there. So you can double click on that, and you can see here under define load combinations, it's brought all that information in from Midas. I'll go in and change our design code to ASHTO and hit the design section button. And once it's run the design, it gives you a wealth of information on the number interaction diagrams, axial moment in both directions. You can look at it by load combination, you can look at it by angle, and obviously it pulls in all the relevant information on this side. You can also look at your moment interaction by load combination or by the concurrent axial force. Again, all the information is over on the side here. But then I really enjoy this view. It gives you a 3D view of the interaction where you can see the axial moment interaction, the moment interaction, and it provides you all of your ratios off to the side for your various load cases. And as you can see, because it's the lower bottom chord, you've got pretty much just axial loads in there, but you can't actually show every single load combination. You get a few where there's a little bit of moment in there. But those obviously are not the controlling, there's almost no load in there. But really a useful tool, and Midas provides a great means of being able to take these custom sections that can be relatively complicated, complex. You can put them together pretty quickly, get them into Midas, get them analyzed, pull them out, and then run your design checks. And you can see we did all that in about, I don't know, 5 minutes. So just one more thing I'm going to mention real quick. Another thing I like about Midas is just the fact that pretty much everything in Midas. You can pull up a table view for it. I find this incredibly helpful, not just because if you want to change a property in a number, you can just select the cell and copy and paste it across 20 others, and it updates like that. If you want to pull information out of Midas, you can export all these as Excel spreadsheets, and you can pull all your results out into Excel and then develop maybe an external check if you want to corroborate what you're seeing in Midas. It provides you a good way of getting that information out in a useful format. And so with that, those were pretty much the main features I was just wanting to go over real quickly with regards to our decision-making process to switch over to Midas for this final portion of the design. Thank you all for hanging in with me, and hopefully you found out a little bit of something, if not about the structure, about Midas that you didn't know before. And I guess if there's any questions, we can knock those out in the few minutes that are left.